Okay, welcome back to the last session of our HoTT workshop 2021. The first speaker in this session is Dan Christensen from the University of Western Ontario with a talk on non-accessible localizations. Thank you, Dan.
Okay, well, thanks to the organizers for giving me a chance to speak here. It's been a very interesting event so far. So I'm going to try to give an accessible talk about non-accessible localizations. So in this talk, I'm going to try to give some background. I'll give some motivation and history for why we study localizations or reflective subcategories in general. And then I'm going to get towards the main result. I have to talk about smallness. So that says when a type is equivalent to a type in some given universe. And then using that, I can give a theorem that gives a localization at a possibly large family. So I've posted in the chat a link to my page that has the slides I'm presenting, it has the formalization, and it has the 2-page abstract. So you can see that in the chat. Okay, so a bit of history. Localizations are really prevalent in topology. They started in the 70s with work of Sullivan and Bousfield. And they play a really fundamental role to try to organize a lot of conjectures in the field and help solve some of these conjectures. I'm just going to mention some very simple examples of localizations. So given a topological space X and a prime P, there's an associated space called the localization of X at P. So we're localizing a space at an ordinary prime number. And what this produces is a space whose invariants have been localized at that prime number. And this tends to make the spaces much easier to study. Calculations are easier. But it's also known that you can combine these calculations for all primes and the rationalization in order to recover information about the original space. So this is sort of the prototypical example, but there's many more sophisticated types of localizations. The word localization is used because this predates infinity category terminology, where we might say reflective subcategory, because this is something like a reflective subcategory, but it's homotopical, and the word that's typically used is localization. It also comes up in the theory of infinity categories, and they're very well studied, these localizations or reflective subcategories. In particular, one thing we know is that every infinity topos is a left exact localization of a category of presheaves. So that kind of statement is very important for studying infinity toposes. And then a very similar situation arises in logic, where you have modalities, which are operations that take a proposition to a different proposition, written with some kind of symbol, like the diamond symbol on the slide here. And this is used to express things like possibility or necessity. But formally, it has a very similar sort of property as the kinds of localizations that I'm going to talk about in this talk. Okay, so that's just a very brief motivation. So let me try to explain precisely the concept that I'm going to talk about. So I'm going to review some results from the Reicher-Schulman-Spitters paper from 2017. And a lot of this is also in the HoTT book. So a reflective subuniverse, L, of some universe in homotopy type theory, first of all, consists of a subuniverse. So there's a predicate on the universe that lands in propositions. There's some function from the universe to itself. And then there's a map from every type X to L of X, where L is this function. And this map has to be a localization, which means the following. The codomain Lx has to be a local type. It has to satisfy the predicate. It has to be in the subuniverse. And this map should be initial among maps to codomain types. So every other map to a local type has to factor uniquely through this one. Of course, I mean uniquely up to homotopy. So one key property is that once you know the subuniverse, if the L and the eta exist, then they're unique. So it's just a property of a subuniverse to be reflective. So one key example of a subuniverse is if you have a type I and an I-indexed family of maps, you can say that a type Z is F local if every map from one of the AIs to Z extends uniquely to the BI. So for every one of the maps in the family and for every map from an AI to Z, you get a unique extension, again, up to homotopy. So one example is where you take a single map in the family, the map from an n+1 sphere to the unit type. And in that case, the F local types are exactly the n types. So that's going to be an example that actually comes up again a bit later. Okay, so at the top here, I've just summarized the things from the last slide, the definition of a reflective subuniverse and the definition of the F local types. And here's the key theorem that's crucial in this subject. So it says that if the indexing type lies in the universe U, and all of the domains and codomains of the maps in the family lie in this universe U, then the F local types, that subuniverse, is a reflective subuniverse. It's usually written L sub F. And this result mirrors many results that are known in mathematics. Maybe the closest thing in topology is a work of Dror Farjun on localization with respect to a map or a family of maps. But it's also known in the situation of locally presentable infinity categories, and there's many other analogs. But the smallness criteria, that the indexing type for the family and that the types belong to that same universe is always present. You always need an assumption like that. So, and a key example of this would be the n truncation, right? We saw on the previous slide that the n truncated types do arise from such a family. The indexing type is just the unit type, and the sphere and the unit type are in every universe. So that means you can form n truncation. That's an example of that theorem. So if you have a reflective subuniverse and you can present it as the F local types for some family, then we say that that subuniverse is accessible. And there's a natural question: is every reflective subuniverse accessible? And this is the sort of question people have studied a lot in topology. And I want to tell you about a classical theorem in topology by Cascoberta Scavenel-Smith. And I'm going to give this in more detail in the next slide, but I want to say it here in brief. They show that for topological spaces, the answer to that question is independent of the ZFC axioms for set theory. Okay, so let me tell you more precisely what they did. So now I'm back to topological spaces, and I made up this terminology to describe the spaces they study. A CSS local space is one that's a one type, and it has the property that when you take group homomorphisms from this group that I'll describe to every fundamental group of your space, you get that there's only one. There's only the trivial group homomorphism. So, and this should be true for every base point, for every cardinal. And these groups here, Z to the kappa is the kappa indexed product of copies of the integers. And Z less than kappa is the subgroup consisting of families where the support has cardinality strictly less than kappa. Seems like a strange thing to choose, but that's the collection of spaces they choose as their subuniverse in our terminology. And here's what they prove. So first of all, they prove that there is a localization onto those local types. So in our terminology, we would say that they form a reflective subuniverse, although there are some subtleties in that translation. The second thing they show is that if that localization is accessible, then a measurable cardinal exists. Now, a measurable cardinal is a cardinal which has a 0,1 valued measure on it, which if the cardinal is called kappa, it has to be kappa additive, and it can't just be focused on one point. It can't be a point measure. So it doesn't really matter what the definition is, but the key point is that the existence of a measurable cardinal implies the consistency of ZFC. So if ZFC is consistent, it can't prove its own consistency. So we certainly can't prove that every localization is accessible, because that would prove the consistency of ZFC. So that's the way they see that the accessibility of every localization is independent of ZFC. On the other hand, if you assume an even larger cardinality axiom called Fopenka's principle, they are able to show that every localization is accessible. So it's so there's relationships in both directions with large cardinal axioms. I'm not going to give the details of Fopenka's principle because it's not relevant for this talk. Okay, so what I'm going to do in the talk is mainly talk about the first point here. Try to reconstruct what they've done to do this localization, and at the same time both simplifying it and generalizing it. All right, so back to HoTT. So we're going to talk a bit about smallness. So we're fixing a univalent universe U, and I say that a type is small if there is a type x prime in the universe U and an equivalence from x prime to U. No truncations here. This is automatically a proposition already. Then we say that a type is 0 locally small. That just means the same as small, but it gives us the first step in an inductive definition. And a type is n+1 locally small if all of its identity types are n locally small. So in particular, a 1 locally small type is a type all of whose identity types are small. And that's sometimes just called a locally small type. Okay, so the key theorem that my results will rely on is a theorem of Egbert-Reika's that uses his join construction. So he shows that if you have a surjective map from a small type to a locally small type, then the locally small type, the codomain X, is in fact small. This isn't exactly how he phrases it, but it follows immediately from what he's done. And I'll just remind the audience that surjective is expressed as -1 connected. And I also have a reminder here that a map is n connected if all of its fibers, when you n truncate them, you get a contractible type. Okay. So the first thing I want to mention is a generalization of Egbert's theorem, which says if you start with any n greater than or equal to -2, and you have an n-connected map from a small type to an n+2 locally small type, then X is small. So when you take n to be -1, this is exactly Egbert's result, and it doesn't reprove it. I use Egbert's result to begin this induction. So when n is -1, we have a -1 connected map, and we have -1 plus 2. We have a 1 locally small type. And so we recover the join construction result. When n is -2, it's even more trivial because 0 locally small is just the same as small, so that it isn't saying anything. But then for higher n, you can prove it by induction based on Egbert's result. So one example of this is that if you take two groups where group G is small, and you take a pointed map between their classifying spaces, so this is KG1 and KH1, these 1 types associated to G and H. If that map is 0 connected, which corresponds to the map on homotopy groups, or the map from G to H being surjective, then BH is small. So that follows, that's the n equals 0 version of this result. And BH will automatically be 2 locally small because it's a 1 type. So it's iterated at any types are contractible. Okay, so, and that makes sense. A quotient of a small group should be small. So that is a consequence of this result. Now, I won't mention it here. In the paper and in the formalization that I'll mention at the end, there's a lot of other results about smallness that aren't needed for the line of this talk, so I'm not mentioning them. But they do come up in some other related results about orthogonal factorization systems. Okay, so now I need a result that allows us to restrict a localization from a larger universe to a smaller universe. So now I have two universes. U is a small one and U prime is a big one. And here's what the theorem says. Again, we have any n at least -2. And we start with the reflective subuniverse of the larger universe U prime. And we assume that the eta map, the localization map, is n connected, at least for all of the small x, x and u, and that Lx is n plus 2 locally small, also for all x and u. If you have those assumptions, then if you look at just the L local types in U, that subuniverse of U is a reflective subuniverse of U. Okay, so let me just give you the quick proof. So using Theorem 1, it's very easy. Because Theorem 1, we've got exactly the hypotheses here. We have an n-connected map to an n plus 2 locally small type from a small type. So it follows that this Lx type is small. And being small means that you can choose something that's in U with an equivalence to Lx. And then you can define the eta for this L prime, I'll call it eta tilde, to just be the composite of the old eta with the equivalence you have between Lx and L tilde x. And then it's easy to see that this satisfies the property of being a localization. So this is not meant to be surprising, or once you know that previous theorem, this just drops out. But it's a nice way to organize the fact that under certain circumstances you can restrict a localization from a larger universe to a smaller one. One thing that's needed here, and that relates to the last talk we saw, is you do need to use propositional resizing, at least if you require the predicate for a subuniverse to land in propositions for that universe, then technically this doesn't form a subuniverse. But if you have propositional resizing, you can do that, or you can just be more flexible in which kind of propositions you allow for a subuniverse. So you have to do one of those two things. Okay, so now here's the main theorem that is the analog of that first point from the CSS result. So it says if you take any family of n-connected maps, and n is some fixed number, at least -2, and you look at the f local n plus 1 types in U, then they always form a reflective subuniverse. And the key here is I didn't say anything about this family being small in any sense. I didn't say anything about what universe the indexing type is in or the types AI and BI. Just pick any family you want, as long as the maps in the family are n-connected. And then when you don't just look at the f local types, you look at the types that are both f local and are n plus 1 truncated. Then they'll always form a reflective subuniverse. Okay, let me go through the proof. So the idea is you take your family and you add one more map to it. You add the map from Sn plus 2 to the unit type. So in other words, we take the indexing type I for the family, and we take the coproduct of that with the unit type to give us one more index, and we send the extra index to this map. Being local with respect to the extended family is the same as being local with respect to the original family, as well as with respect to this map. But the example from earlier shows that being local with respect to this map is the same as being n plus 1 truncated. So we're really studying the types that are local with respect to this extended family. So now let's just pick a universe that contains our given universe and contains this family f bar. So it contains the indexing type for it and all the domains and codomains. And let's just look at the localization that we know exists on U prime using the RSS result. Because relative to U prime, this is a small family, so the f bar local types there are reflective. Now the key step here is that in the paper by myself, Opie, Reika, and Skokola, there's a theorem that says because all of the maps in this family are n-connected, the localization maps that we get for this localization are also all n-connected. So for the maps in F, we assume they're n-connected, and you can just check this map is n-connected. So it follows that all of these maps are n-connected. Also, these targets here, they're all n plus 1 types, and an n plus 1 type is always n plus 2 locally small. So that means we can apply the previous theorem. We've got n-connected maps to n plus 2 locally small types, so we can restrict the reflective subcategory to the smaller universe using the previous theorem. Okay, so let me show you how this recovers the result due to Cassacuberta, Skevinals, and Smith. So if you apply this in the infinity topos of spaces, where you take your family to be this large family of the classifying spaces of all the quotient groups that appear in their statement, then being local with respect to that family turns out to be exactly equivalent to the condition on homotopy groups, that they have no maps from this group. And they also require the local types to be 1 types. So this is the n equals 0 case of this theorem. And these maps are 0 connected. And so it follows that you can do the localization with respect to that family without having to go to a higher universe. Okay, so the results I've talked about are all formalized using the HoTT library. Now, the one thing that's interesting to mention is how this proof compares to what Cassacuberta, Skevinals, and Smith did. And it's simpler than their proof because we work with the 1 types directly rather than trying to pass to homotopy groups and groupoids and worry about base points and such things. So it actually makes the proof cleaner, the methods shown here. As I mentioned, it's more general. And one way is because it applies to n+1 types, not just to 1 types. And another way is that it applies in any model of HoTT, not just to spaces. The formalization, the proofs I've sketched are pretty short, but the formalization is around 1,100 lines. And that's because a lot of background needed to be filled in. In particular, this result due to cores wasn't formalized, and that's been done now. And it needed a bunch of other results. Some results about orthogonal factorization systems were needed. And also, mirroring comments from the last talk, one of the big issues was dealing with the universe levels and universe variables in COC. That was a fair bit of work. Let me see, I think that's all I wanted to say, so I'll just stop here and say thank you very much.
Dan, let's give a round of applause. Are there any questions for Dan? As always, you can put your question in the chat or raise your hand and I will admit you.
As Milena said, I'm going to not go to a breakout room right now, but at the end of the session, I'd be happy to be in a breakout room if anyone has any questions then that they think of, between now and then.
There's one question by Ali.
Hi, can you hear me?
Yep.
I just wanted to ask, how does this relate to the measurable cardinal stuff that you mentioned in the beginning? Does this mean we can say stuff about ZFC?
So I didn't formalize anything about that aspect of the result, but it certainly follows that if we could prove in HoTT that this was accessible, then it would follow that it was accessible in spaces, but we know that you can't prove that. So that's why I call it a non-accessible localization. And there's a few delicate steps you have to think about to see that chain of logic. But it would be nice to actually understand measurable cardinals and try to directly see that if you assume this localization at this family is accessible, try to see some taboo arise or something that we shouldn't expect to be provable arise. That would be nice, and I'm hoping to be able to do that.
Thank you. We have another question from David.
Yep, go ahead.
Hi, Dan. This is really cool stuff. I'm wondering about the possibility of sort of resizing principles for locally small or n locally small types. Like, given that I guess you've proven under conditions that they are equivalent to small things, do you think there's any hope for something where we just say that, like, if you're so much locally small that you are in the universe already?
No, in fact, one of the results that I didn't mention is that an n-type is small if and only if its homotopy groups are small.
Oh, very cool.
Yeah. So, and more generally, an n locally small type is actually small if and only if its first n or so homotopy groups are small.
All right, great. Yeah. Thank you.
Okay, are there any other questions? Have I missed anyone who raised their hand? No. Okay, then thanks again, Dan, for this wonderful and very pedagogical talk.
No, thanks for having me.
Thank you. And we will have a small break of 4 minutes until the next talk starts. So see you there.